Okay, let's go ahead and get started. I want to welcome you to the second installment of Unit 14. This is General Equilibrium. We are going to need a calculator and something to write with, so if you don't have those, go ahead and get those handy, and we will get started. All right, well, in our last installment, we looked at some general concepts concerning equilibrium, and what we said was that equilibrium meant that the forward and the reverse reaction were the same. And we looked at an equilibrium constant, and we called the equilibrium constant, we might have called it K, or we called it Kc for concentration, or we called it Keq. So all of those are the same. But then we looked at another K when we were talking about partial pressures or pressures of gases, and we call that Kp. And so what I want to begin with in this installment is how we relate Kp to Kc, or K. And as it turns out, there's a very simple relationship between these two. And that relationship is that Kp is equal to Kc times RT in parentheses times delta, or to the delta n power, to the power delta n. Okay? So this is a very important equation that we're going to need to relate Kp to Kc. Now you might be thinking, well, wait a minute, isn't Kp and Kc the same? Well, there is a situation that we're going to look at in just a few minutes in which Kp and Kc is the same, but not ordinarily. So let's take a look at this relationship and how it can help us to relate Kp to Kc. So the first thing we're going to need to do is we're going to define some things. First of all, there is an R in this equation right there. Well, we've talked about a number of different R's. Which one is it? Well, the one that we're going to be using in this equation is the gas R. There's no energy units in this equation. So we're going to use the gas R, which is 0.0821 liter atmospheres per mole per degree Kelvin. So you remember that from our gases unit, 0.0821 liter atmospheres per mole per degree Kelvin. Now that, of course, dictates that the temperature component of this equation must be in Kelvin degrees, so we'll remember that. Now what about this delta N business? What do we mean by delta N? Well, it's simple. It's the change in the number of moles of gas. So we've got Kp is equal to Kc times 0.0821 liter atmospheres per mole per degree Kelvin times the temperature in degrees Kelvin times the change in the number of moles of gas. So let's take a look at a specific problem and use this equation to help us to figure out that relationship. So here's the problem. It says at 1100 degrees Kelvin, Kp is 0.25 for this reaction. So we've got 2 moles of SO2, it's gas, plus 2 moles of O2 gas in equilibrium with 2 moles of SO3 gas, right? So that's the equilibrium there. And they're giving me the Kp value, and they want to know what Kc is. How do we figure this out? Well, remember the basic relationship between Kp and Kc is this one up here. Kp is equal to Kc RT delta N. So let's write that down first. So we have Kp is equal to Kc RT delta N. And by the way, be sure that the parentheses include only the R and T and not the Kc. So now let's plug the Kp in. We've got 0.25 is equal to Kc, of course. Let's plug in our R, 0.0821 liter atmospheres per mole per degree Kelvin. We're told that the temperature is at 1100 Kelvin. Now, let's talk a little bit about this delta N. Remember that delta N is the change in the number of moles of gas. Here's what's critical. When we do change in N, it has to be final minus initial. Okay? Or another way to say that is products minus reactants. So how many moles of gas do we have on the product side? 2, right? And we don't have to actually calculate the number of moles of gas. We can just use the coefficients to help us to know what the number of moles of gas are in the balanced equation. So 2 on the right-hand side. How about the left-hand side? Well, we've got 2, and then of course there's an understood 1 right there. I'll put it right there. So that's 3 moles of gas on the left-hand side, on the reactant side. So 2 minus 3 then. So now let's solve. So it's algebraically, we'll just do this multiplication, raise it to this power of -1. When we divide that by 0.25, I get 22.6. Now I want 2 significant digits, right? Because I only have 2 significant digits here. So only 2 significant digits. So I'm going to round my 22.6 to 23. So what have I just determined? I've determined what the K is, or the Kc. By the way, we'll assume that if there's nothing there, that's Kc. So Kc is if the Kp is 0.25 and the temperature is 1100 Kelvin. Okay, that's how we use that relationship. Now, the next thing is I want to talk to you about a little trick, and that is this. Folks, always check the delta N before you start a problem involving the relationship between Kp and Kc. The reason is this. If the delta N happens to be 0, okay? If the delta N happens to be 0, remember that what's going to happen is that all of this, right, the Kc, all the RT to the delta N, anything to the 0 power is 1, which means that Kp would be equal to Kc. So you can save yourself a lot of trouble if you simply check, and it will often happen, for example, on the AP exam, that the Kp and the Kc will be the same, and you won't have to do a calculation if the delta N is equal to 0. So check that first. Okay, I hope that makes sense. Now, what happens to the K? Let's talk a little bit about manipulating the K. What happens if I change the reaction, or I change the equilibrium? So what happens to the value of K if we reverse the reaction? So you recall that we had this reaction right here, H2 plus I2 yields to HI. And when we did that in our previous part for this notes, we said that the K value for that was equal to 50, right? So we said that K is equal to 50. We wanted it to 2 significant digits, so we put a decimal. I'll put a little decimal right there too. Okay, so now, and the H2 concentration was 0.012. The I2 concentration to equilibrium was 0.15, and we said the HI value was 0.30 molar. By the way, go back in your notes. If you forgot this problem, go back and look to see how we solved this problem. But the important thing is that we got a K value for this equation, for this equilibrium as written, of 50, right? Of 50. But what happens if, for example, let's move on, we reverse the reaction? What happens if we reverse the reaction? Well, so this is the reverse reaction now, relative to the one we saw before. This is the reverse reaction. Products become reactants, reactants become products, okay? And so what happens to the K value? Well, remember that K is always equal to products over reactants, right? So if I reverse the products and the reactants, then I should fully expect for the K value to be the reciprocal. So if I want to know the new K value, I'll call this K prime, all right? I want to know the new K value for this new reverse reaction. It would be 1 over 50 or 0.20, right? So we've learned something now. If you reverse the reaction, then you take the reciprocal of the K to get the new K for the new reaction, the reverse reaction, okay? All right, let's move on. Well, what happens if we cut all of the coefficients in half, right? Then we will have this reaction, 1/2 H2 plus 1/2 I2 yields HI. That was a 2 previous, now it's just HI, right? So what will the new K be, right? What will be K prime for this reaction? Well, here's what we're going to remember. You can, by the way, think of this as dividing everything by 2, but I prefer that you think of it as multiplying everything by 1/2, because that 1/2 becomes the power to which the K is raised. So if the original K was 50, the new K is 50 to the 1/2 power, right? 50 to the 1/2 power is the same thing as saying the square root of 50. Anything to the 1/2 power is the square root of 50. So when we do that on the calculator, we get 7.07. 7.07 then would be the new K prime, right? So if we reverse the reaction, we take the reciprocal of the K. If we cut the reaction in half, we take the square root. If we divide everything by 3, then we take the cube root and so forth, okay? All right, so we're just working on manipulating K now, right? What happens when we change the equilibrium in some way? All right, let's take a look at this one right here. What if we add up equations? Then what? How do we handle the K's? Well, then we multiply being the operative word here, we multiply the respective K values. Now, let's use everything we've learned about K's to solve this problem that's a little bit more complicated. So here we go. We've got some equilibrium constants for these reactions right here. This is, by the way, determined at 550 degrees, right? So remember, K values are only a certain value for a certain temperature. If you change the temperature, you change the K. So we've got this first reaction here, as shown, and its K value is 67. We've got a second reaction, so this is the first reaction, and we've got a second reaction that has this K value of 490, right? Two different reactions, and from these two reactions, we want to create a third reaction. We're interested in another reaction. Let me see if I can get them both on the screen at the same time. I don't think I can. No, I can't. Okay, so I want to calculate the K at the same temperature, 550, for this commercially important gas shift reaction. I'm interested in the K, I'll call it K3, for this reaction, H2O gas plus CO2, or CO rather, gas, in equilibrium with H2 gas and CO2 gas, right? So what do we do with these two equations that I've been given? Well, the first thing I'm going to do is I'm going to reverse the first reaction, the one that I labeled number 1 above, this one right here. I'm going to reverse this reaction. I need to reverse that reaction so I can cancel things out properly. So once I reverse that reaction, what happens to the K? Well, when I reverse that reaction, its K value is its reciprocal, right? So the new K value is 1 over K1 or 1 over 67, because it was originally 67, now it's 1 over 67. But I'll leave the second one alone, okay? So the K2 for this one was originally 490. Guess what? It remains 490, all right? So leave that one alone. Now, let's see what we can cancel, right? So we've got two reactions, and we want to cancel what we can on the right and the left. Here's how it works. CO solid on the left of that one, CO solid on the right of that one. COO solid here and solid there cancel, and look what I'm left with. H2O gas plus CO gas yields H2 gas plus CO2 gas. That's exactly what I was looking for. So I've got two reactions that if I add up, right, I can get the reaction that I'm interested in, right? I can get the reaction that I'm interested in. So what do I do with these two K values once I've got the two reactions that I'm interested in and I've canceled out what I need to get the reaction that I'm hoping for? I'll call it K3. I'm going to remember multiply these two numbers together. So 1 over 67 times 490, when I do that on the calculator, I get 7.3. So I've been able to then manipulate the equations or the equilibriums to get to the equilibrium that I was interested in. And remember the equilibrium that I was interested in, remember, was this one here. Okay? So this is the one that I was interested in. I was able to arrive at that by manipulating those two equations. Again, reversing the first one, leaving the second one alone. And then I add up the two equations. When I add them up, I multiply the two delta H's. Excuse me, I'm sorry. I'm thinking about thermo. I multiply the two K's, and in doing so, get this value of 7.3. That'll do it for this one. I'll see you in the next. Thanks. Bye-bye.